Now let's take in problem based on work energy principle. So problem based on work energy principle. principle. So here I am just writing the problem. A 1.6 meter diameter cylinder of weight 1.5 kilonewton is shown in figure starts from rest starts from rest and rolls freely rolls freely towards the right because of the because action of 400 Newton weight. Determine the velocity of the cylinder and of the weight after the weight has moved 8 meter in downward direction. Neglect friction and weight of the pulley and weight of the pulley. Now I am drawing the diagram here. Here there is a frictionless surfaces here. Now I am having a cylinder here touching here, that is surface point O. This radius is 40 centimeter and this radius is 80 centimeter. It's connected with the help of the spring here. This one is the pulley and the other end is connected with 400 Newton load. All the surfaces are frictionless. Weight of the cylinder is given, that is 1.5 kilonewton. Now we have to find out velocity of the cylinder and velocity of this cylinder. So now we have to apply work energy principle. So we can calculate first work done. So work done is nothing but force into displacement. So here this block is responsible for doing work because it is moving in the downward direction 8 meter. So force is 400, displacement is 8, will be 3200 Joule. So the work done in that case will be 3200 Joule. Now we have to find out change in kinetic energy. So one by one I will find change in kinetic energy of block of weight 400 Newton. So here I can write 1 by 2 mv square, that is final kinetic energy, 1 by 2 mu square, that is initial kinetic energy. And in the problem it is mentioned the final and the initial kinetic energy is 0 because it is starting from rest. So now we are having 1 by 2 into m. The weight is given 400, so m is 400 divided by 9.81 and we can write v square. So this one is the change in kinetic energy of block of weight 400 Newton. Now change in rotational kinetic energy of cylinder. So we will have 1 by 2 I omega square minus 1 by 2 I omega naught square. Omega is final velocity, omega naught is initial velocity. As mentioned in the problem, initial kinetic energy for both block and cylinder is 0. So omega naught will be 0. So initial rotational kinetic energy of cylinder will be 0. So now we are having change in rotational kinetic energy of cylinder is 1 by 2 omega square. So now here we are interested in I and omega. So I am again drawing the diagram here which is mentioned in the problem. Here we are having the cylinder and here this radius we are mentioning 40 centimeter and this radius we are mentioning 50 centimeter. Weight of the cylinder is 1.5 Newton. Here point O where cylinder is in contact with the surface. String is going like that. You pass through a pulley and the second end will be here at 400 Newton attached to the 400 Newton load. So here this distance we are having 40, here we are having 50. And now if you see this cylinder will rotate above this O, at this point O. So if we are considering this point as a point of rotation for this cylinder, then we have to consider moment of inertia. So we know the moment of inertia of any cylinder at, at the axis passing through the center of the cylinder will be mr square. Now we are interested in moment of inertia. Oh, so here we are interested in moment of inertia about an axis passing through O. Through O. So it will be, that is moment of inertia at A plus mr square. So I will be, and we know Ia is nothing but mr square by 2 plus mr square. So we will get 3 by 2 mr square. Now we are having the value of I, that is 3 by 2 mr square. So I can write I 3 by 2. We know the weight of the cylinder, that is 1.5 kilonewton. So this will be divided by 9.81. So we will get the mass. And radius, we know this is 0.8. So 0.8 square. So we are having the expression, that is 3 by 2, 1.5 into 10 to the power 3 divided by 9.81 into 0.8 square. Calculate it, it will come 146.8 kg per square. So the moment of inertia cylinder about a O will be 146.8 kilogram meter square. Now we are interested in value omega. Here omega is nothing but V by R. So R we know, that is 0.4. So here I am considering 0.4, but here I took 0.8. So let's see the diagram here. Here if you see, this string is connected with a radius of 0.4. So if I am considering this one as a V, so we have to consider the corresponding radius. So omega for this case will be V by this R, that is 40. So that's why I am considering V divided by 0.4. So it should be clear. We have to consider the radius corresponding to the linear velocity. That's why here the radius r corresponding to v is 0.4 in the diagram. So I am taking radius 0.4. Now we can easily apply the work energy principle. So now let's apply the work energy principle. Now apply the work energy principle, that is work done equals to change in rotational kinetic energy of cylinder plus change in translational kinetic energy of block. So now we are having work done, we have already calculated, it is 3200. Change in rotational kinetic energy of cylinder, it is nothing but 1 by 2 pi s square, and that is change in translation kinetic energy of block 1 by 2 v square. 3200, we know I is 146.8 and omega we have calculated in terms of V divided by 0.4 plus 1 by 2 m here is 400 divided by 9.81 into V square. So now 3200 we are having, if we calculate this thing, we are having 458.75 V square plus 20.39 V square. So now we are having 3200 equals to 479.4 V square. So V square will be 6.7. So V will be square root of 6.7. We will get 2.58 meters per second. So that is the linear velocity of the block. So now we are having linear velocity of the block, that is 2.58 meters per second. So if we know the linear velocity of block, so we can calculate omega, because we know omega equals to v by 0.4. So 2.58 divided by 0.4, we will get 6.45 radian per second. So this one is the angular velocity of the cylinder. And now if we want the velocity at the circumference of the cylinder, then we have to use this omega and corresponding r. So velocity, or we can say that linear velocity at circumference of cylinder of radius 0.8 meter. Now we are having v to omega r. So omega we know 6.45, to multiply with 0.8, then we can get 5.16 meters per second. Now we are having the linear velocity at the circumference of the cylinder of radius 0.8. Here I am considering 0.8 because I want the velocity corresponding to the radius 0.8. So with the help of work energy principle, we can easily find out the values of V. Let's take another problem based on law of conservation of momentum. Problem based on law of conservation of linear momentum. So I'm just writing the problem. Two railway trucks of masses 10,000 kg and 8,000 kg moving in the same direction in the same direction at a speed of 10 meter per second and 15 meter per second respectively, collide and subsequently move together. Now we have to calculate common speed due to impact. So I'm again repeating the problem. Two railway trucks of masses 10,000 kg and 8,000 kg moving in the same direction with their speed 10 meter per second and 15 meter per second respectively collides and subsequently move together. We have to find out common speed due to the impact. So now let's solve this problem. This problem is based on law of conservation of linear momentum. So let's draw the diagram first. Here we are having the mass 10,000 kg and it is moving with a velocity 10 meter per second. Another truck which is having the mass 8,000 kg and it is moving in the same direction with 15 meter per second. And now they are colliding and moving together. So now the total mass is 10,000 plus 8,000 and they are moving with the velocity. So there are two scenarios. This one is the before collision, and this one is the after collision. So here the net force acting on the system is zero. So we can apply the law of conservation of momentum, that is initial momentum of the system plus final momentum of the system. So first find initial momentum of system. Momentum system. So initial momentum of system, we have to take mass and corresponding velocity. So 10,000 and it is moving in positive x, so 10, so it will be 1 0 0 0 0 kg meter per second. Similarly, for that is initial momentum of system, or we can say it is initial momentum of 10,000 kg mass. Similarly, initial momentum of 8,000 kg mass will be mass, that is 8,000 into speed will be 15. So it will come around 120000 kilogram meter per second. So the initial momentum of system, it includes 10,000 kilogram mass and 8,000 kilogram mass is 1000000 plus 1200000, and if we calculate it, then we get 2200000 kilogram meter per second. So now talk about final momentum of system. And final we are having 10,000 plus 8,000 into V. So we are having 18,000 V. So now according to the law of conservation of linear momentum, initial momentum, that is 2200000 will be equals to final momentum, that is 18,000 V So V will be 220000 divided by 18000. And if you solve it, we will get 220 divided by, we will get 220 divided by 18, and if we solve it, we will get 12.22 meters per second. So the correct answer is 12.22 meters per second. Let's take an interesting problem based on law of conservation of energy. So problem based on law of conservation of energy. It's a very interesting problem. I am just writing the problem. A truck weight 150 kilonewton is traveling with 2 meter per second velocity. It impacts with a buffer spring which compresses 1.25 centimeter per 10 kilonewton. Find maximum compression of the spring. So now we have to find out the maximum compression of the spring. I am here just drawing the rough diagram. Truck weight is 150 kilonewton. It is just impacting with this spring, and now we have to find out the maximum compression of the spring. So now let's solve this problem. Here the kinetic energy of the truck will convert into the elastic potential energy of the spring. So according to law of conservation of energy, kinetic energy of truck will convert into elastic potential energy of spring. So for finding elastic potential energy of spring, we are interested in K, that is stiffness. So spring stiffness equals to K is nothing but force divided by deflection or deformation. So here we are applying 10 kilonewton force and deformation is 1.25 by 100 meter. So if we calculate K, we come 800,000 meter. So this one is the spring stiffness for the buffer spring. So now for elastic potential energy we can use this K. So now kinetic energy of truck we can calculate with the formula 1 by 2 mv square. So now 1 by 2 weight of the truck is given, so we can find out the mass 150 into 10 to the power 3 divided by 9.81, and V is given in the problem, that is 2 meter per second, so 2 square. So if we calculate this thing, so this thing will come 30581.04 joule. So now according to law of conservation of energy, kinetic energy of truck equals to elastic potential energy of the spring. So we can write 30581.04 equals to 1 by 2 K and maximum compression, that is we can see X max. So now we can write X max equals to square root of 2 into 30581.04 divided by K. So now we are having 61162 divided by K, that is 800,000. So the maximum compression we can get 0.2765 meter. So in centimeter it is 27.65 centimeter. The correct answer for maximum compression will be 27.65 centimeter. So by applying the law of conservation of energy, we can easily find out the values of unknowns in such kind of problems.